Dear friends, I would be discussing three important year standard cycles. Namely, one is what is known as the Otto cycle, the other is referred to as the diesel cycle, and the third one is what is known as the dual cycle. So, the objective of this short lecture is to understand the various processes in the Otto, diesel, and dual cycle and learn how to represent those processes on the pressure volume diagram and the temperature entropy diagram. So, let us begin with what is known as the Otto cycle. So, Otto cycle refers to four setup processes. So all these thermodynamic cycles, you know that they are basically setup processes which get you back to the initial state. So the Otto cycle, which is an ideal cycle for a petrol engine, comprises of four processes. The process 1 to 2 being isentropic compression, process 2 to 3 being the constant volume heat addition, the process 3 to 4 is what is known as isentropic expansion, and finally the process 4 to 1 is the constant volume heat rejection. So these four processes in this order would be called as the Otto cycle. So let us learn how to represent them. So let me draw the pressure volume diagram. So this is the pressure and this is the volume. Let me just correct this. This is the pressure and this is the volume. Okay. So in your compression process, you know that the pressure would increase from the initial pressure. So the initial pressure for the engine is closer to the atmospheric conditions. So it would be about atmospheric pressure and it would be about atmospheric temperature. So the state 1 would be the temperature being almost equal to atmospheric pressure, and the temperature being atmospheric temperature and the pressure being atmospheric pressure of 1 bar. Okay, so there the volume is equal to the total volume inside the cylinder. You know that these processes would in reality be executed in an engine. Okay, so when the engine is at the bottom dead center, then the volume occupied by the gas would be the total volume, and that would be equal to V1. 1 to 2 would be the compression process, and the compression process would be in a manner which is P into V raised to gamma is equal to constant. So it would be a curve which obeys the law P into V raised to gamma is equal to constant, and the compression would end at the volume equal to the clearance volume. Okay, so this volume V2 would be the clearance volume. So this point 2 is over here. This is V2 and V2 is equal to the clearance volume. The V1 is equal to the total volume. Okay. The next process is the heat addition process, which is at constant volume. So when you say it is a constant volume, it has to be a vertical line on the pressure volume diagram. Okay, wherein the volume at 2 is equal to volume at 3, and the pressure would increase from P2 to P3. Right? So this is 2 to 3. Constant volume heat addition, meaning volume V2 is equal to V3. Okay, and the pressure would increase. The next process is isentropic expansion. Again, it would be a curve which would obey the law P into V raised to gamma is equal to constant, and the expansion would continue till the piston gets back to its initial state, that is the top dead center. Okay, so when that is the bottom dead center, so the piston would again come to bottom dead center. It was initially at bottom dead center, then it reaches top dead center, then there is a heat addition, again there is an expansion where the piston would come back to the bottom dead center, and this would be an expansion phenomena following the law P into V raised to gamma is equal to constant, which is the law for an adiabatic process. You know that isentropic means it is an adiabatic process of a special kind. It is a reversible adiabatic process. Okay, so reversible adiabatic. Now the final process in the cycle is 4 to 1. So 4 to 1 is again at constant volume. So you see over here that V1 is equal to total volume is equal to V4, and this has to be a vertical line on a pressure volume diagram because this is a constant volume process. Okay, there is a heat rejection, so the pressure would decrease, right? The same process can be represented on a temperature entropy diagram. So let me just quickly represent this on a temperature entropy diagram. 1 to 2 would be vertical. Why it would be vertical? Because the entropy remains constant during isentropic compression. So S1 is equal to S2. And why the temperature would increase? The temperature would increase from T1 to T2. But why it would increase? Because of compression. So T2 would be greater than T1. So this is 1 to 2. Then there is a heat addition, and you know that when there is a heat addition, the entropy would increase because of heat addition from S2 to S3. S3 would be greater than S2. So the process would be like this. This is 2 to 3, and the entropy has increased from V2 to V3. Okay, so this is the representation 2 to 3 on the temperature entropy diagram, where I am moving along the constant volume line because it is a constant volume process. Why the temperature is increasing? Temperature is increasing because of heat addition. So temperature T3 has to be greater than T2. Why is entropy increasing? Entropy is increasing because of heat addition. Then there is a isentropic expansion. Because of expansion, the internal energy would decrease, the temperature would decrease. So the temperature drops down, and because the entropy remains constant, so S3 is equal to S4. So on a temperature entropy diagram, it would be a vertically downward line. So 3 to 4, and then finally 4 to 1. So this is the representation for the 4 to 1 process. 4 to 1 is what? Constant volume heat rejection. Heat rejection, entropy would decrease. So S4 would be greater than S1, or S1 would be less than S4. Why the temperature decreases? Because there is a heat rejection. Heat is rejected, so temperature would decrease. Heat is rejected, so the presentation of Otto cycle on pressure volume diagram and temperature entropy diagram. So in the next lecture, I would record and discuss the diesel cycle representation and the dual cycle representation.